I'm Maia Teegarden, and today I'm extremely excited to introduce you all to Turbopack. You briefly heard about it in today's keynote, but I'm here to take you on a much deeper dive. First, I'll introduce myself real quick. I originally joined Vercel last year as a core Next.js developer, and one of my main efforts was replacing our file transformer Babel with SWC, which is a much faster alternative written in Rust. And earlier this year, I became the engineering manager of a newly formed team focused on web tooling. We maintain SWC, Webpack, and now Turbopack. Now, I'm sure you're all excited to hear about what Turbopack is and what makes it so special, and I will get to that. But first I'm going to start with a little bit of history, because I think looking back at the way JavaScript-based apps have evolved, especially over the last 10 to 15 years, helps illustrate what it takes to build a bundler that will stand out today and stay useful into the future. So let's go all the way back to the pre-JavaScript days, back when everything was statically rendered by servers. When you typed a URL into the address bar, a server would return a page of HTML that would stay the same until you either clicked on a link or submitted a form. And these actions would result in the server sending back an entirely new page of HTML that would repaint the entire screen. Then JavaScript came along, and you could update HTML on the page dynamically. This started out really basic, like showing scrolling text or sparkles that trail your mouse cursor. But over time, websites became more and more interactive, and more JavaScript was added to the page. Eventually, the lack of a module system became a problem for maintaining large JavaScript codebases. You could split your code into multiple files, but they all had to share a global scope. Bundling JavaScript just meant concatenating files. Node.js really changed the game, even though it was a server-side runtime. It came up with a module system called CommonJS, and it bundled itself with a package manager called npm. Now you could organize your code into modular files and easily pull in reusable third-party dependencies. This inspired what we now know as bundlers, tools that could understand module systems in order to build a dependency graph and create bundles of JavaScript which combine these files with a runtime so they could run in the browser. Another monumental change came in 2015 with ES6. Previously, JavaScript, also known as ECMAScript, was very slow to make changes. There had only been one release in 16 years, and it was pretty insignificant. But ES6 came out with a bunch of revolutionary changes, and the ECMA committee planned to add new features yearly. The problem was it was going to take some time for browsers to support these features, but developers wanted to use them right away. This is where Babel came in, which was originally called 6-to-5 because it would take ES6 code and transform it into ES5 code. So bundlers took on more responsibility and started to support transformations. This also allowed developers to use languages or supersets that can compile down to JavaScript, like CoffeeScript and TypeScript. Bundlers empowered JavaScript-based apps so much that they went from little widgets on server-rendered pages to what are now known as single-page apps, or SPAs. The server would send down some minimal initial HTML with JavaScript that would render the entire application once it loaded. Naturally, this led to bigger JavaScript bundles, which can take a long time to load. To help with this, bundlers started supporting something called code splitting. Instead of one big bundle, there would be many chunks that could be lazily loaded as they are needed. For example, if you're loading page A, you don't need the code that renders page B until you navigate to it. The concept is pretty simple, but with large apps, this can get really complicated to create optimized bundles. Client-side rendering did wonders for interactivity, but admittedly also introduced some weaknesses. The main issue is that sending down an initial HTML page with just a loading state is an awful experience for both search engines and end users. Search engines crawl initial HTML to determine the content and structure of the site, but there's nothing there, so the crawler assumes the website is empty. Humans are also not big fans of loading pages. The longer they have to wait, the more likely they are to give up and leave. So server-side rendering, now known as SSR, became popular again. But with Node.js, you can take a hybrid approach and use the same code to render on both the server and the client. While this approach is better for search engines and end users, it definitely adds a lot of complexity for developers. This is when frameworks like Next.js popped up to abstract this complexity away from application developers. Frameworks are so powerful because they cohesively combine solutions for routing, data fetching, and bundling in a way app performance is almost a given. While SSR is an improvement, there's always room for innovation. One of the newer approaches on the block is called React Server Components, which introduces zero bundle size components that only render in the server. You no longer have to send the entire component tree down to the client. You can send down only the pieces needed for interactivity, leading to much smaller client bundles. Again, this creates a better experience for end users while adding complexity for developers. And I think this trend is inevitable. Sometimes innovation comes from simplification, but more often it comes from developing increasingly advanced techniques. What's key is bringing the community along and ensuring these innovations can be widely adopted. Okay, that brings us to present day, so we're done with the history lesson. I've been talking about bundlers in general so far, but Webpack has been top dog for a while now, comfortably since Next.js chose to build on it in 2016. It was the natural choice then, but the evolution of web development is beginning to stretch Webpack to its limits. It simply wasn't designed for the size and complexity of apps that we're building today, and it's getting incredibly difficult to stay on top. Lately, there have been more and more bundlers cropping up to compete. Based on their marketing, they are all focusing on better performance. Vercel first came onto the scene claiming to be blazing fast with incremental builds. Vite sells itself as the next generation of front-end tooling because of its lightning-fast HMR, regardless of app size. ESBuild blew everyone's minds with its order of magnitude faster builds and rightfully dubbed itself an extremely fast bundler. Tobias, the creator of Webpack, joined Vercel last year as well, and we spent a lot of effort squeezing better performance out of Webpack. We made a lot of improvements, but eventually we started to see diminishing returns, so we evaluated some of the newer bundlers like Vite and ESBuild. Vite's main selling point is that it has lightning-fast HMR. It accomplishes this by not bundling source code, and just uses the browser's ES module support. This makes updates really fast because it's only transforming a single file, but we found that this has a negative impact to the startup times for large applications, because it causes a flood of network requests that get bottlenecked by the browser. After improvements to Webpack, Vite actually took longer to open a page. While Vite was faster for updates, Webpack was still under half a second for most real-world applications. And for production builds, Vite uses Rollup, which is in the same performance ballpark as Webpack. It's also not ideal that Vite works completely different in dev than it does in production. And based on these results, it didn't seem worth the migration. ESBuild blows Webpack and Rollup's production build times out of the water. But ESBuild openly admits that the primary reason it's so fast is because it has made architectural decisions for the sake of performance that may make the code harder to extend. It works well for the use cases it was designed for, but if you want to do something different and it doesn't fit with the architecture, you're pretty much out of luck. One relevant example is HMR, which is a key Next.js feature we don't want to lose. So far, all efforts have failed to implement it in ESBuild plugin land, and Evan, the maintainer, doesn't seem interested in building it as a core feature. We could fork ESBuild to mold it to our purposes, but it would be difficult to rip apart and reform something so tightly integrated. It seemed risky that it might be too rigid to easily adapt to future innovations that Next.js will want to support, like React Server Components. We knew that migrating Next.js to another bundler was going to be a lot of work, so the rewards needed to be worth it. Ideally, we could improve the application developer experience, the framework developer experience, and the user experience with one tool. But we looked and that tool didn't exist, so we decided to build something new. Improving the application developer experience mostly boils down to build performance. We want to keep developers in flow, and waiting for pages to open, updates to reflect, and production builds to deploy just ain't it. It's also really annoying for things to go wrong and you don't know why. Maybe you're seeing a really long and cryptic error message, or you're not seeing your changes until you refresh the page, reload the server, or clear the cache. These are all experiences we want to free application developers from. We also want to allow developers to extend our bundler. We recognize that one size does not fit all, and we need to be able to accommodate different requirements. Improving the framework developer experience means making the bundler easier to work with. Right now there is a lot of complexity involved with implementing SSR and React Server Components on top of Webpack, and it's complexity that every framework has to repeat. Ideally, we could build something more composable that would lead to better reuse. It should be possible to create reusable bundling paradigms on top of bundlers. We care a lot about developers, but the user experience trumps all, because that's who we're ultimately building for. They deserve applications that are fast to load and quick to interact. Bundlers can help by creating the most optimal bundles possible, whether that's advanced tree shaking or evolving new and improved bundling patterns. Bundlers can also help guide application developers fall into the pit of success by warning them when they stray from the golden path. So based on our goals and the things we wanted to improve, we agreed on some design tenets. What we came up with is that our bundler needs to be adaptable, fast, and scalable. And this may start to make it clear why we decided to name our new bundler Turbopack. Turbopack is adaptable because it shines for development and for production. This is a bit aspirational because we're focusing on the development workflow right now, but we're not stopping there. You won't have to use two different bundlers for development and production. Turbopack can also handle client-side rendering, hybrid SSR, static site generation, and React server components. Some of these are specific to React, but it should just as easily handle any other framework. Again, this is a bit aspirational because we're still prototyping our API, but we know the bundling strategy will be flexible, and that's something that really sets Turbopack apart. Another huge goal is that Turbopack will not leave the Webpack ecosystem behind. We recognize that Webpack's extreme popularity comes from how extensible it is and how it empowers third-party tooling. We are committed to playing nicely with existing tooling and supporting the capabilities that Webpack developers are used to as best we can. Turbopack is fast because we've designed it from the ground up for speed. We have an incredibly talented team, and when you combine our knowledge, we have decades of ideas about how to build a faster bundler. We have designed for the big and complex apps that developers are building today. One example I can give is lazy compilation for development. You only need to build what you need once it's requested. Next.js built lazy page building behavior on top of Webpack, but now it's built into Turbopack. Another example is dev-optimized bundles. Production builds are optimized for weak devices on slow connections, but developers are often on powerful machines where the server lives on the same machine as the browser. It doesn't make sense to analyze the entire graph for development. Just bundle what's needed for the page. It's a little risky that the bundles don't exactly match what you see in production, but modules switch bundles all the time. What's important is that the bundle runtime is the same for both environments. Turbopack is also fast because it's built on Rust, which is a native language known for its performance. For the longest time, JavaScript tools have been built with JavaScript, because these tools are being built by JavaScript developers who are trying to make their lives easier, and Node.js allowed them to do that. But Rust is just inherently better at the task at hand, and SWC has paved the way as a solid foundation for Rust-based JS tooling. We're betting on Rust as the future of JavaScript infrastructure. Building something fast is cool, but even fast tools can become slow when they're building something huge. And if history has taught us anything, codebases will continue to grow for the foreseeable future. We didn't want to build a tool that would get linearly slower with the size of the codebase. We wanted something that would scale. Build time should correlate to the size of diffs and not the size of projects. This is a concept known as incremental computation. Don't rebuild what you've already built. Just rebuild the changes. The idea of an incremental build engine is not completely new. Personally, I implemented a pretty rudimentary example of this in the bundler parcel called the request tracker that I aspire to take further. This was before I was getting into Rust, and discovered the Rust compiler had a similar demand-driven query system, which led us to the library Salsa, which is inspired by Rusty's query system and is used in Rust Analyzer. If you look at the Turbo engine implementation, it is actually very similar to Salsa, because we did talk to Nico and got a deep dive of Salsa. We ultimately decided to build our own thing because we had slightly different goals, and we wanted to have more control over the design and the roadmap. But Nico deserves a huge shout out. This incremental computation is the main selling point of Turbo Repo, but Turbo Repo caches tasks at the package script level. We wanted to support this incremental behavior within Turbopack to support more granular bundling tasks. And if we were going to rebuild this functionality in Rust, we wondered if we could build it as an abstraction that could be reused by Turbopack, Turbo Repo, and possibly any other tool we decided to build in the future. We wanted to create an version of control where instead of the build system controlling the tools are controlling the build system. So essentially we wanted to build an incremental build engine. So we thought it appropriate to name it the Turbo Engine. Now, a deep dive into how the Turbo Engine works could probably use its own talk, and I promise someone on the team will deliver on that eventually. But today I'm just going to give a quick high-level overview of the concepts. The Turbo Engine is responsible for distributing and caching tasks, where a task is the combination of a function and the values it receives. Functions can also output values that other functions receive, and the engine builds up a task graph of these relationships. When the engine detects that a value has changed, it re-executes only the functions that depend on that value. Those functions may produce new values, which could cause a cascade of function re-executions. The engine travels up the task graph until no functions need to be re-executed. The tools that build on the engine get to decide which functions are cached. And there will be different cache layers, so tools may decide that some functions should be cached in memory, but only some functions should be cached to the file system. Currently only the memory layer is supported, but we plan to add a persistent cache in the future. Alright, hopefully it's clear we put a lot of thought into the design and architecture of Turbopack. Now I'm going to dive into those exciting benchmark numbers you heard about in the keynote. We've started out focusing on development, so the two measurements we are paying attention to are starting up a dev server that loads an HMR ready page and HMR updates to a page. The bundlers that support HMR that we are comparing are Turbopack in Next 13, Webpack in Next 12 and Next 11, and Vite. Let's talk about HMR updates first. This is where the Turbo Engine really pays off, because we're only rebuilding one file that has changed. We are 700 times faster than Webpack and Next 12 for a page with 20,000 modules, and we are 10 times faster than Vite. 20,000 modules may seem extreme, but we wanted to test the limits. Turbopack truly maintains lightning-fast updates, regardless of app size. Now let's look at the dev server startup benchmark, and we'll replay the demo with the example app from the keynote. You can see that Turbopack finishes well before the rest. Turbopack does so well here because it is written in Rust and lazily does as little work as possible for just the page that is requested. But it performs much better than Vite because it still does some basic bundling to avoid throttled network request. You can also see the work we did to improve Webpack from Next 11 to Next 12, which already gave it an edge over Vite in this metric. I spent a long time talking about how awesome Turbopack is, but I do need to spend some time bringing everyone back to earth to remind you that this is still an alpha release. We spent a lot of time working on the core architecture and benchmarking infrastructure to prove we were building something fast and scalable. But to be very honest, it hasn't had much battle testing for day-to-day use. We were really excited to share what we've been working on and wanted to include the community in on the progress sooner than later. So please be aware that there will be some rough edges. We've got a whole team devoted to bringing not just a better experience for the Next.js community, but a true successor to Webpack for the broader community. Please check our docs for information on the status of supported features and known issues, and stay tuned for improvements. As for what to look forward to, we have a lot planned for the future. First, we plan to make Turbopack more than just a dev bundler by bringing production build support to Next.js. Next, we plan to make Turbopack more than just a Next.js bundler by providing a stable API and partnering with other frameworks. It's going to be a long road, but we aim to make Turbopack the true successor to Webpack by helping the community port the ecosystem. And beyond Turbopack, we're excited about the potential for a whole suite of turbocharged tools built on the Turbo Engine. Alright, well, I hope this helped you understand what's so special about Turbopack and what we've got in store for you here at Vercel. And before I go, I just want to give a huge shout out to the web tooling team. I'm incredibly excited about everything we're working on, and I'm so grateful to be a part of it. But that's all I have today, so thanks so much for watching, and I'll see you all next time.